Thanks, moderator, and thank you all for attending this session. So today we'll discuss about how to exploit a GPU on Spark, more specifically for the machine learning workloads. And it will be good if you can tweet about this session using this hashtag RIS9SAIS. Okay, so about me. I'm a principal engineer at IBM Systems. I have a long time career on operating system development, mostly on AX and Linux kernel development. Then I moved it to big data side, working on optimizing Apache Spark for the power systems. So this work item is actually a result of that activity. And currently I'm focusing on distributed deep learning and machine learning workloads for power systems, exploiting GPU and NVLink. And I'm also the committer for the GPU enabler, the package which we are going to deep dive today. And my contact details are there here, my GitHub and email IDs. So here is a detailed agenda of what we are going to talk. So we will start with why we need to use a GPU for Spark. And then later we go on how do we use our software packages to easily exploit the GPUs in the Spark workload. So we have two options. One is to load the custom developed CUDA. Suppose if you developed a CUDA program and you wanted to use it in a distributed Spark manner, then you can use one of our packages to easily implement that. The other option is to let the software package to generate a CUDA program for you. And then we will move on to how do we write an efficient GPU program in Spark. My colleague Ishizaki will explain on that, focusing on the data parallelism and data format importance. And we will also give a little bit deep dive on how do these two packages are implemented. So before we go on to exploiting GPU on Spark, I would like to give a little bit of overview of what is GPU and what is CUDA, so that will help to understand this better. So first, GPU. So we call it as GPU, that is general purpose graphic processing unit. So this is almost similar to CPU in the sense that it will also let you to execute a program which you have written, like CPUs. But the major difference is it is specifically designed for parallel processing. See, for example, in CPU, you maximum get some 30 or 40 cores at the most. You can create 40 threads together in a single processor in the high-end CPU. But in GPUs, we get thousands of cores. For example, latest V100 has 5,000 odd cores available in a single processor. So you can run 5,000 threads simultaneously on the GPUs. So the catch is CPUs depend for a single thread performance. So typically you measure the CPU performance as how much of time an individual transaction takes to complete. But when you come to GPU, your performance is how many transactions you are completing in a single second. So that is kind of a throughput processor. There is a major difference between CPU and GPU. And other thing is this GPU comes as a separate card like our regular graphics card. So the programming model will be a little different because it cannot directly access your memory, and then it is not directly working on your operating system. They had a separate device driver model, so you have to do a lot more activity than the regular CPU program. We will have details about that as well. So other important software package is CUDA. So in the CPU world, we have numerous compilers and loaders and the runtime environment for different languages. So in the similar way, CUDA is for the GPU world. So it lets you to write a program which can be executable on the GPU in the high number of cores, and it provides all the facilities to load the GPU kernel and execute those things. So if you take a typical GPU program, so let's say if you wanted to, for a very simple case, if you wanted to run a program which will multiply an array by 2. In the CPU world, you typically write one instruction to multiply an individual element by 2 and put a for loop for 1,000 or 1,000,000 times, depending upon how many elements you have. But in case of a GPU world, you will also write a single line, like to multiply one element by 2, but you will start executing thousands of threads. So instead of putting a loop for 1,000, you create 1,000 threads which will execute the same instruction. So this GPU is a little bit slow for individual instructions. So let's say if this GPU says 10 times slower for multiplying a single element. So, but it will execute 1,000 threads in parallel compared to CPU. So even if it is 10x slower, in effect, you will get 100x faster than CPUs. That is a major advantage. The only catch is your programs will be embarrassingly parallel so that you will be able to write your algorithm in a very parallel way. So that is what here kind of this code here is written here. That is a typical GPU CUDA code to do that array multiplication. So other aspect is once you written this CUDA program, this will be executed on GPU, so which cannot access your CPU memory. So you need to take some additional steps. So you need to copy your data from your CPU memory to your GPU memory, and then you need to load the kernel to the GPU and execute it, and then retrieve back the result data to you. So we have one more feature available in the latest GPUs that is called UVM. So that is kind of helping you to avoid this data copy, but still there will be more complexities about the data format. If you wanted to exploit a GPU in Spark, the Spark world, all your data is in a Scala objects. But in the GPU world, it understands only C and C-related objects. So you need to convert your Java object into C structures and then execute in our GPU. In addition to that, the Spark world is a record type. It takes one record, processes it, and goes to another record. But here you can see it is not it's a columnar data type in GPU world. You need to get all the data together at the same time and execute the instruction on all the data at the same time. That is called the SIMD instruction. So those kind of things also you need to take care of. So pretty much it is a little bit lot of code whenever you wanted to exploit GPU on a Java world or a Spark kind of systems. So we will see how our packages helps you to speed up those programming. So now you might understand why we need to club Spark and GPU. The Spark kind of, we all know it's like a very good parallel processing systems which schedules the jobs across thousands of nodes. But whereas a GPU is a very good parallel processing processor which will help you to execute thousands of threads within a single node. So when we combine this Spark and GPU together in a heterogeneous system with GPU, you will get really best performance, that is a lightning fast performance we can get it. Okay, so how do we exploit this GPU and Spark? So we kind of propose two methods. One method, you write your own CUDA kernel, and then we will execute that CUDA kernel in a simpler way. And other is we have modified Spark, which will help you to generate, it will automatically generate the CUDA kernel for you. You don't even need to write the CUDA kernel. So the first one is invoke the hand-tuned CUDA kernel. So for which we are proposing a package called GPU Enabler. It's an open source package. So this is implemented as an add-on package for Spark. So you just need to download this jar file and put it on your path, and then it will automatically add new operators to your RDD or data set. Then you can simply use those operators in your data set to invoke the GPU programs. And then it will internally take care of all the complexities I was mentioning previously, that is converting the data, loading the kernel, and getting the data format, changing between the Scala objects and C objects, everything. So it is available in this GitHub links. You can take it once we upload this PPT. So if you look at an example, so we write one CUDA kernel. So this is the same example I was telling, that multiplying an array by 2. That is a step 1. And the second step is you write the Spark program. So this is where our importance comes in. So you just simply have one first URL point to your PTX. PTX is nothing but the compiled CUDA program. Then you kind of create one wrapper for your CUDA function. So here we created a function multiply by 2. So you just simply create one wrapper called ds CUDA function, and then simply pass those wrapper function to your map function in your data set or RDD. So what happens is whenever this map function is called, then it will identify that the input function pointer is a CUDA function pointer. Then it will automatically generate the glue code, whatever is needed to copy the data between here and there and execute it. And then this glue code will be a Java code. We kind of extended the code gen functionality in the existing Spark to generate this Java code. Then it will compile automatically and then execute it for you. So here you are doing it with just a couple of lines of code, but believe me, if you have to write everything, it will be hundreds of lines. So here, the automated code generation for CUDA is helping you to skip all those code and make the execution is much smaller with just a couple of lines. And then the third step is, as usual, you have to compile your Scala program and execute it. But one more step is you have to compile your CUDA program as well to get the PTX. So from the performance wise, so we kind of implemented logistic regression in CUDA. So we got about 3.6x for a single GPU. So this is on the toy data set, which runs for, let's say, 60 or 70 seconds. But when we take a real complex algorithm and put it on real data, you will get some much better benefits. So this is run on the IBM Power Systems in a single P100 GPU. So the next one is automatically, so here we did a three-step process where we kind of compiled the CUDA program and then used a Spark program to execute it. With the transparent acceleration, we don't need to write the CUDA program. The code gen, whatever I am talking about, it will generate the glue code. In addition to it, it will also generate the CUDA code for you and compile it on the fly. So here we kind of modified the Spark. So here we need to use a custom Spark to exploit the transparent execution. And then it will provide a new operator, select, express, and reduce, kind of overloading the existing operators. So whatever the expression you are passing to these operators, those mathematical expressions will be converted into CUDA GPU operations, and then it will be executed transparently without needing for you to write any CUDA code. So it will always looks like you are simply writing a Java code, but everything is taken care behind the scenes to run it better on GPU. So this is available at GitHub IBM Spark GPU. You can download it. So then obviously it also takes care of all the complexity I was mentioning in addition to generating this CUDA code. So here the two-step process became, three-step process became just 2 steps. You write your data program, Dataframe program. So here you mentioned that select, you are doing a multiplication of 2 operators in the regular way how you are doing it. And then when you compile and submit it, everything will be taken care internally for you. So now this multiplication will be executed on the GPU. So we wrote a vector multiplication program and benchmarked it. And we were able to get 1.7x improvement for that example. Then the next topic would be towards faster GPU code, where my colleague Ishizaki-san will kind of explain the need for having a data parallelism for your program to exploit GPU, and then also the importance of data format. And then he will also give a high-level overview about the implementation details of both the framework, that is using the GPU enabler and also the IBM Spark GPU. I'd like to welcome Ishizaki-san to take over from here. Thanks.
So until now, so Madhu give an overview of GPU execution and how two approaches is used from the user view. So from now, so Madhu give a short brief overview. So what is the design and how two approaches works from the data movement view and GPU code generation view. So here is my brief introduction. So I'm a researcher at IBM Research. So my technical background is a compiler optimization. So I'm working for IBM Java virtual machine over 20 years. In particular, so I led the research and development for Java just-in-time compiler on PowerPC platform. So I'm an active contributor to Apache, open source Apache Spark. Mainly, I'm contributing to CKL and core modules. I'm also a committer of the GPU enabler. So, so here I'd like to talk about how what is an important factor to make a GPU code faster. So we think there are 2 items. One is that it is important to assign lots of the parallel computation into GPU cores. The other is that it is important to reduce a number of the memory transactions into GPU hardware. So regarding first, so I'd like to talk about why it is important to assign lots of the computation into GPU cores. So GPU can achieve the high performance as you already seen in the HPC area, deep learning area. So this is because GPU has a lot of the core. Also GPU, all of the GPU core is very busy. So in that situation, so GPU can achieve a very high performance. On the other hand, so if GPU, if only some of the GPU core is busy due to the sequential program, so GPU can achieve a low performance. On the other hand, if you can see the right-hand side, so every core is busy if we can assign the parallel program into GPU core. So we can achieve the high performance by using a GPU core. So it is therefore it is necessary to achieve the high utilization of GPU. So the second part, so why it is important to reduce number of the memory transactions. So in the middle, so there is a one sample program. So this program has 8 load instructions. But it depends on the memory layout with even if with the same program, number of the memory transaction means into the access to the physical memory hardware. So number of the transactions is different. So in the right-hand side, you can see the column-oriented layout. So if you in the GPU, if we use a column-oriented storage, so GPU can reduce the number of the memory transaction. So this is because GPU, in general, GPU has a hardware to coalesce contiguous memory access into one memory transaction. But there, in this case, so 4 memory transaction, 4 memory load can be coalesced into one memory transaction. On the other hand, if you see the left-hand side, so this is a row-oriented layout. So in this case, so memory access is not contiguous. So therefore, we are seeing the more memory transaction compared to the column-oriented approaches. Here, so here is now we talked about 2 items. So first item, so in Spark, so Spark program already has a Spark program has been already written by the set of the parallel operation like map, join, filter, reduce. So each of the operation has a semantics. Each element in the operation can be executed in parallel. So therefore, if the data size is enough big, so Spark program has enough parallelism to be executed on GPU. In the second part, so columnar storage can achieve better performance on GPU. So existing paper already proves the k-means case. It is so columnar storage approach can achieve 3 times faster compared to the row-oriented storages. Here we have 2 questions. So how can we write a parallel program for GPU? How can we use columnar storage for GPU in Spark? So regarding the first question, so thanks to Spark parallel programming. So Spark already, as I already explained, so Spark programming model implies lots of the parallelism in the program. So therefore, if we follow the Spark programming semantics, so we can assign lots of the computation into the GPU. So therefore, from the next page, so I'd like to talk about the second question. So next section, I'd like to talk about how two-frame works from the data movement view and code generation view. So here is a figure for so GPU enabler. So regarding the data movement. So GPU enabler basically handles the RDD. So RDD exists in the Java heap by using the row-oriented storage. So when GPU enabler knows that RDD will be used in the GPU, so GPU enabler starts data conversion from the row-oriented storage to column-oriented storage. In the same time, so GPU enabler moves the data from Java heap to off heap. So this is because the current GPU driver supports the data transfer from the CPU of heap to GPU. So now, we assume the data exists in off heap with a column-oriented storage. Then, we copy the GPU enabler copies the data from the CPU to GPU. After that, the two map operation can be executed in the GPU. After that, GPU enabler do the same process in reverse order. So copy to the GPU to CPU, then go back to the RDD. Finally, we get the data computed on GPU in the RDD. That's the mechanism of how data is moved from the CPU to GPU, so back to the CPU. So the important point is that these complicated processes are automatically done by GPU enabler. So therefore, user doesn't take care anything about this. So these processes are hidden from the user. That means transparency that we are saying. So in GPU enabler, how to write a program? So here is a Spark side. So we write a kernel. GPU. We write a map operation as a launcher of the GPU kernel. In the GPU kernel, we write map semantics by assigning the data for each array element. So next, I will talk about data frame approaches. So here is a data movement in the data frame approaches by automatic code generation. So in the current Spark, so data frame cache operation. If data frame cache operation is performed, the data is stored as a column-oriented storage. So that's a good part for GPU, but it's still in the Java heap. So we enhanced the Spark to store such a cache into the off heap. So this is because we want to reduce the overhead between the data movement between off heap and Java heap. Now we have data on the off heap as a column-oriented storage. Then we can copy the data from CPU to GPU. After that, we apply the two map operation by combining into one GPU kernel. After that, we do the same things in reverse order. I mean, copy to GPU to CPU. Again, in this approach, we can also hide these operations from the user. So this copy operation is done by enhanced Spark automatically. That's an advantage from the user for ease of the programming on GPU. So in the automatic code generation approach, so how to generate a GPU code? So in the session, in the morning session, Databricks guy said catalyst optimizer. So catalyst optimizer can accept data frame program, then generate a Java program to be executed on the JVM with some optimization. So we newly added a new path in the end to generate a GPU CUDA code like current catalyst does. So CUDA code is generated for the kernel operation. In the Java side, so we enhanced the coordination to generate a data copy and launching the kernel operation. So here is the last page. So we talk about three things. So how we can accelerate your workload by using a GPU on Spark, and then how to use a GPU on Spark. So we introduce two approaches, GPU enabler or automatic coordination. Finally, so we talk about how these two approaches work from the data movement view and coordination view. So this approach is not achieving the best performance by top-notch programmer. So this approach tries to lower the bar of the GPU programming on Apache Spark for non-expert. So thank you for attention.
Are there any questions?
Hello. How fast is data being copied from CPU to GPU?
Sorry?
How fast is data being copied? What's the performance? What's the speed of data being copied from CPU to GPU?
Do you mean?
How much overhead?
We are not introducing any new overhead over there. So that is how much of the hardware provides we can use the same performance. So if you look at this, okay, with IBM Power we have a new pipeline called NVLink. So that will provide a much better speed than regular PCA speed. If you go for Intel, you will get the PCA 3 or PCA Gen 4 speed.
I had a question regarding the benchmarks that you show. What was this cluster size? I didn't quite get it on the...
I think it's written that the small blueprints over there. I think it's 1 million records, and you can look at it, some 8,500 features and iterations and stuff. It's a very small set. It's like a artificially generated data set.
Right, but cluster size? Number of
sorry,
worker
single
nodes.
node.
This is
Single node, single GPU. Okay.
Do you have any benchmarks for a distributed?
No, but we have tested that functionally this GPU enabler works on a distributed mode in a heterogeneous environment, but we haven't done any benchmark on that. But we welcome if anybody could try that out. Thanks.
Thank you for the talk. I appreciate the wanting to make it easy for the non-expert developer. I was wondering, you're using the primitives of Spark to take advantage of the model. Given this, is there any kind of addition to the Spark primitive that would make using the GPU even more efficient? If there were some other primitives that you could add?
So the one thing we would like to have Spark is if Spark can have the awareness of GPU during scheduling. Say, for example, in a heterogeneous environment, few nodes will have GPU, few nodes may not have. So then the user can specify, okay, if I wanted a GPU nodes, then it can schedule only on the GPU. So that feature we are expecting will help any kind of GPU expert, and not just our GPU, but overall for heterogeneous environment. That we are expecting, let's say.
Next, so in your automated GPU execution, right? Do you have a list of primitives that you have already accelerated, which I can go ahead and use directly?
Oh, map and reduce.
Okay.
One more question?
So you had mentioned about writing CUDA code and then compiling it and then writing a Java code for running Spark. Have you guys ever thought about or tested on PySpark where you can write CUDA code directly in Python?
The code generation will be in the internal engine. PySpark is kind of a wrapper on top of the existing Scala engine. So, but we haven't provided extension for PySpark so far, but we welcome some open source contribution. That is one of the reasons for submitting this paper as well.
Any more questions?
Do you have data for more broad set of application?
Not yet. Yeah, that's good point. Yeah, we want to add more benchmark.
Okay.
Regarding the code automatic generation for Dataframe APIs, right? Can you handle all the case, or just some code generation works, some doesn't work, or everything works fine now? For the Dataframe Spark GPU code auto generation for CUDA, can it handle all kind of case? Like auto generate all kind of application code?
No, it's for a small subset. He's asking about whether the fully transparent CUDA can generate for all kind of expression. This one.
Yes. Yes. Can you support all Dataframe APIs?
Are you talking about the operation?
Okay.
The expression, what kind of expression we are supporting? So I think we are supporting the primitive expressions as of now.
Yeah, now these operations are supported.
All arithmetic operations are supported as of now.
Okay, thanks.
Any more questions?
Thanks for the talk. Knowing the overheads of memory copy in GPU, wouldn't you think that it might make sense to actually work on Catalyst to also transform the logical plan? Because you know that some things might be better computed at the CPU end so that less data needs to be copied over at the GPU layer. So the logical plan as well as in the Catalyst cost optimizer, don't you think you guys should bring the GPU perspective into it?
That's a good point because if that particular operator or instruction set is not fit for embracingly parallel, we will do it for CPU. But here we are not so because here we are expecting the user to specify wherever there is a GPU acceleration needed. So that can be a part to where a COB based optimizer can decide on that.
Awesome. Thank you. Thank you very much. So one more round of applause for the speakers, please.
Thank you.